27% of the universe has been measured to better than a percent by people who have never once caught a piece of it. That's not a turn of phrase. 5 separate methods, sharing almost no assumptions between them, land on the same amount of missing mass. They've been agreeing for decades, and the agreement gets tighter every time somebody builds a better instrument. Nobody knows what it is. Not approximately. The leading candidate had a natural range of properties it was supposed to have, and that range hasn't been narrowed down over the years. It's been emptied out, detector after detector, by finding nothing. And this isn't some curiosity in a back corner of astronomy. Every mass ever quoted for a galaxy, a cluster, or the universe itself comes out of one equation. Either there's unseen matter propping those numbers up, or the equation is wrong, and every weight it has ever produced falls over with it. 90 years in, what physics is holding is a number with nothing behind it. If that sits badly with you, subscribe and leave a like. And tell me in the comments what city you're watching from and what time it is there right now, because it makes no difference at all to what follows. The stuff we're about to talk about pours through your room at the same rate at 3 in the morning in Lisbon as at noon in Jakarta. It keeps no clock, and it has no schedule. I'd like to know anyway. Now, the strange part about the local picture, it dominates the universe. There is almost none of it here. Add up every scrap of dark matter inside the orbit of Neptune, the whole solar system, the sun included, out past the last planet, and the total comes to roughly the mass of one decent-sized asteroid. A single rock. That's the entire dark matter content of everything you would call home. Meanwhile, it's going straight through you as you sit there. Billions of particles a second across a target the size of a person, arriving at something like 400 kilometers a second, each one crossing your body in under a millionth of a second. And nothing happens. At the absolute upper limit still permitted by experiment, perhaps 10 of them clip a nucleus somewhere inside you over the course of a year. 10. In a year. You have never felt one. Nobody has. Nobody ever will. And that's the whole difficulty. In one sentence. The thing that built the shape of the universe barely touches the room it's standing in. So how does anyone know it's there? The answer starts with a swarm of galaxies in the constellation Coma Berenices and a set of photographic plates from 1933. The Coma cluster is a genuine physical object, not a chance alignment. More than 1,000 galaxies, bound to each other by gravity, orbiting a common center the way a swarm of bees orbits nothing in particular. Each galaxy is on its own path through the group. Some are coming toward us, some going away. And the difference shows up in their spectra as a shift in the position of known absorption lines. Fritz Zwicky, working at an observatory in California, had spectra for 8 of them. 8. He measured how fast each was moving relative to the group as a whole, and the spread came out so wide that a galaxy at that speed would cross the entire cluster in a small fraction of the cluster's age. Then he asked the obvious question: what does it take to hold something together at those speeds? The logic is the same as launching a rocket. A galaxy on the edge of a cluster is in a gravitational well, and it either has enough speed to climb out of that well, or it doesn't. The depth of the well depends on how much mass is down there. So you can run it backwards, measure the speeds, and you learn the mass required to keep those speeds bound. Then you measure the mass a second way, independently. Add up the light from all the galaxies. Assume each solar mass of stars puts out roughly as much light as the sun does, and multiply. That gives you the mass you can see. The two numbers didn't just disagree. They disagreed by a factor of 400. At the speeds Zwicky measured, The visible matter in Coma isn't holding anything. The galaxies should have scattered, and not slowly. They would have dispersed into the surrounding void long before the light now arriving at Earth ever left the cluster. There would be nothing there to photograph. Instead, there are more than 1,000 galaxies sitting in a tight, obvious, gravitationally bound cluster. He wrote that the cluster must contain a great deal of matter that gives off no light, and he used a German phrase for it: Dunkel Materie. Dark matter, which is a slightly unfortunate name because the stuff doesn't block light or absorb it or dim it. It ignores light completely, and light ignores it back. 4 years later, he published a short note, pointing out that a cluster's mass ought to be readable from the way it bends the light of galaxies lying behind it. Almost nobody paid attention, and he went back to hunting supernovae, which is what he's actually famous for. And that's roughly where the subject sat for 40 years. Not because anyone had refuted it, because a discrepancy in one cluster based on 8 spectra is exactly the kind of result that quietly gets shelved. Something was probably wrong with the assumptions. Clusters might not be stable at all. Maybe Coma was in the middle of falling apart and had simply been caught mid-collapse. For what it's worth, that spread of speeds from 8 galaxies sits within a few % of the value you get today from more than 1,000 of them. The measurement was fine. Nobody wanted the conclusion. What finally forced the issue came from a completely different direction, and from objects nobody expected to be strange at all. Ordinary spiral galaxies. The kind that appear on posters. This is what should happen inside one. Our solar system is the clean case. Nearly all of its mass sits in the Sun, right at the middle. Mercury tears around in 88 days. Neptune crawls, taking well over a century. The farther out you go, the slower things move, and the fall-off follows a precise curve because everything out there is orbiting the same lump of mass sitting behind it. A spiral galaxy looks like it should behave the same way. The light is concentrated in the bulge and the inner disk, and thins out as you go outward, until, past a certain radius, there's essentially nothing glowing at all. So, beyond the visible edge, stars and gas clouds should be orbiting a mass that's stopped growing, and their speeds should drop off exactly the way Neptune's does. In 1970, that assumption ran into Andromeda. The instrument was an image tube spectrograph, a device that amplified faint light enough to get spectra out of objects that had previously been too dim to work with. The targets were glowing clouds of ionized hydrogen scattered across Andromeda's disk. 67 of them, from close in to as far out as the technique could reach. Each cloud emits its sharp, known wavelengths, and the shift in those wavelengths gives you its velocity. Plot all of them against distance from the center, and you have the galaxy's rotation curve. The curve didn't come down. All the way out to the limit of the data, the clouds were moving at essentially the same speed as material far closer in. That result alone could have been an artifact of where the optical data ran out. The check came from radio. Neutral hydrogen gas radiates at a wavelength of 21 centimeters, and that gas extends well past the last stars in a galaxy, sometimes twice as far. Radio telescopes followed Andromeda's rotation out into that gas, into a region with no starlight in it whatsoever. Still flat. By the late 70s, it was no longer one galaxy. One radio survey published rotation curves for 25 of them. Optical work on high luminosity spirals came out a few months later. Flat, 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 flat. Whatever this was, it wasn't a quirk of Andromeda. Put yourself out there, past the last spiral arm you can see. Behind you is every star in the galaxy, the whole glowing disk, all of it interior to your orbit. Ahead of you, in the direction you'd call outward, there's nothing. No stars, no arms, no light. And you are sweeping around the center at the same speed as material sitting halfway in. There's only one way that happens. The mass has to keep increasing as you move out, in step with the radius, through a region where the light stopped increasing a long time ago. Out where there is visibly nothing, there is as much mass again as in everything you can see. So galaxies are heavier than they look, and clusters are heavier than they look. And the obvious answer was sitting right there. Faint, ordinary matter.
It's not a silly idea. It's the first thing any reasonable person says. The universe is full of things that weigh a lot and shine very little. Burnt-out stellar cores, cold gas that's too chilly to glow, failed stars that never got hot enough to fuse hydrogen, black holes left over from dead stars. Lump them together, and you get what people started calling massive, compact halo objects. Dead, dark, ordinary. And if enough of them are scattered through a galaxy's outskirts, the rotation curves are explained, and everyone goes home. And the idea is testable. The test is one of the cleanest in astronomy. A compact mass drifting across your line of sight to a distant star bends the light passing around it and focuses that light toward you. The star brightens smoothly, then fades again, and the fade is a mirror image of the rise because the geometry is symmetric. More importantly, gravity doesn't care about wavelength. The brightening is identical in blue light and in red light, to the last decimal. Nothing else does both of those things. Variable stars change color as they change brightness because they're changing temperature. A symmetric, colorless brightening is a signature that can't be faked, and the duration of the event tells you the mass of the invisible object that caused it. So they went looking. Tens of millions of stars in the Magellanic Clouds, monitored night after night for the better part of a decade, waiting for one of them to flare up in that unmistakable way. One survey found a handful of candidate events where a halo made of such objects should have produced many dozens. Another watched for nearly 7 years and came up with exactly one candidate. Between them, they left almost no room. Whatever holds galaxies together, dark, ordinary objects can supply only a sliver of it. And then the idea died a second time, harder, from a completely unrelated measurement. In the first few minutes after the Big Bang, protons and neutrons fused into light elements. Deuterium, which is hydrogen with a neutron attached, is a fragile intermediate step in that process. It gets made, and then it gets burned into helium. How much of it survives depends very sharply on how crowded the plasma was. Denser plasma means more collisions, which means more deuterium destroyed. Thinner plasma leaves more of it behind. The amount of deuterium in ancient, unprocessed gas clouds is therefore a direct readout of one number: how many protons and neutrons the universe contains. Not how many of them are glowing. How many are there at all? The answer comes out at about 1/20th of the total contents of the universe, which settles it. Whatever the missing mass is, it isn't made of protons and neutrons. Not cold gas, not dead stars, not rocks, not planets, not black holes left behind by stars. There aren't enough of those ingredients in existence, lit or unlit. Whatever it isn't built from the same things you are. Take a second with that one. Everything you have ever touched, every element on the periodic table, every atom in every object anyone has ever weighed. That's the 20th. The rest is something else. And it brings us back to where this started, and to a problem in the founding measurement itself. Zwicky's factor of 400 was wrong, not fabricated, not sloppy, wrong, for a reason nobody involved could have fixed at the time. To convert what you see in a cluster into an actual mass, you first need to know how far away the cluster is, and in the 1930s, distances came from the measured expansion rate of the universe. That rate, as published, was too large by nearly a factor of 10. That put every galaxy far closer than it really is, and made every galaxy far fainter in absolute terms than it really is, and dragged the whole calculation off with it. With distances we now trust, Coma's missing mass comes out closer to 50 times the visible matter. Still enormous,
Still impossible to explain with stars, but not 400. The strangest part is how long the bad number lasted. The correction wasn't difficult, and the arithmetic was open to anyone. It sat there because the distance scale had Edwin Hubble's name on it, and for a decade and a half, nobody in the field thought to question a number of his. So the founding measurement of dark matter was overstated, defended by reputation, and correct anyway. And notice what that whole episode depends on. Every mass in this story rests on knowing how far away things are. The cluster, the galaxy, the missing fraction, all of it. In 1933, nobody did. Distances did get sorted out over the following decades, measured a dozen independent ways by people who no longer cared whose name was on the old scale. What didn't get sorted out was the dependency sitting underneath all of it. Every mass in that story was inferred from motion. Watch something move. Assume it's in a settled orbit. Reason backwards to the gravity holding it. That works beautifully when the assumption is true, and produces garbage when it isn't. And you can't check the assumption from the outside. A cluster that's quietly falling apart and a cluster that's bound look identical in a snapshot, which is exactly the objection that let people shelve Coma for 40 years. The way out had been sitting in print since 1937, in that short note about reading a cluster's mass off the light of whatever lies behind it. Mass curves the space around it, and light follows the curvature. That's not a metaphor for something else happening. The path is bent because the geometry is bent, and the effect had been confirmed on starlight grazing the sun during an eclipse. A galaxy cluster sitting between you and a much more distant galaxy acts as a lens. It takes light that would have missed you entirely and turns it toward you, and it distorts what arrives. When the alignment is close, you get the dramatic version. The background object gets smeared into a long, thin arc wrapped around the cluster core, or split into 2, 3, 4 separate images of the same thing, sometimes closed into a complete ring. The first confirmed case turned up in 1979. A pair of quasars sitting suspiciously close together on the sky with identical spectra, which is to say, one quasar and 2 paths. 5 years after the man who proposed the method had died, giant luminous arcs in clusters showed up in the following decade and sat unexplained for a while. Then their spectra were measured, and that settled it. The arcs were background galaxies, at completely different distances from the cluster smearing them. The dramatic version is rare. The useful version is everywhere. Most background galaxies aren't well aligned with anything. They're just slightly stretched, a fraction of a percent, far too little to see in any single image. But galaxies are randomly oriented on the sky. Their long axes point every which way. So if you measure the shape of every faint smudge in a wide field and average their orientations, the random part cancels, and any leftover alignment is signal. Around a mass concentration, that leftover alignment is tangential. Everything faintly combed into circles around a center where there may be nothing luminous at all. Done over a large enough patch, that gives you a map of mass rather than a map of light. And crucially, it asks nothing about motion. It doesn't care whether the cluster is settled, collapsing, spinning, or exploding. Gravity is bending light right now, and the bending is what you measure. This is now industrial. A single early week of observing with a wide-field space telescope delivered tens of millions of galaxies and hundreds of strong lens candidates. That survey is designed to end up with the shapes of billions of them.
Cluster after cluster, the maps show the same thing. The mass sits where the galaxies sit. More of it than the galaxies can account for. But centered on them, spread out around them, tracing them. Except in one system, where it doesn't. Two galaxy clusters, catalogued under a string of numbers and known to everyone as the bullet cluster, ran into each other. Head on, and, by a piece of luck that makes the whole thing readable, almost exactly across our line of sight, rather than along it. We're looking at the collision from the side, like a diagram. The light we receive left the system about 3.5 billion years ago. The collision itself was already over when that light departed. The two clusters had passed through each other roughly 150 million years earlier, and were still coasting apart. So what arrives is a snapshot of debris in flight, taken long ago, of an event that had already finished. X-ray telescopes see the hot gas, and what they see is a blunt wedge of it, with a shock front standing ahead of it. The same shape that forms in front of anything moving faster than sound through a medium. The density jump across that shock gives you the speed of the front, about 4,500 kilometers a second. Now, what happens when two clusters collide? The galaxies barely notice. A cluster is overwhelmingly empty space. The galaxies inside it are tiny targets separated by huge gaps. And when two clusters interpenetrate, essentially none of them hits anything. They sail through and keep going at whatever speed they had. The gas cannot do that. Gas is continuous. It can't pass through itself. The two gas clouds slam together, compress, heat violently, and stall in the middle, while everything else carries on. That detail matters more than it sounds, because the gas is not a minor component. In a cluster, the hot gas outweighs all the stars in all the galaxies several times over. It is the ordinary matter. The galaxies are the garnish. After the collision, you have a system where the normal matter has been physically separated from everything else. The gas sits in the middle, glowing in X-rays, where the crash happened. The galaxies are out on either side, well past it. Then you build the lensing map from the stretched shapes of hundreds of background galaxies and ask where the mass is. It's out with the galaxies, both clumps of it, on both sides, offset from the gas by a wide margin, far more than any measurement error. The mass and the matter came apart. You can see the gap. Two pictures. One shows the stuff, the other shows the gravity. They don't overlap. This is the observation that closed a door. Because up to that point, you could always argue the other way. Perhaps there is no unseen matter, and gravity simply behaves differently over large distances than the equations say. That's a serious position, and it explains a great deal. But whatever you do to a force law, the force still has to originate at the matter. Rewrite the equation however you like. Make gravity stronger, or longer ranged, or scale dependent, and the pull still comes from where the stuff is. Here, the stuff is in the middle, and the pull is out on the wings, where there's almost nothing to make it. There's a second result buried in the same picture. The unseen mass went through the collision without slowing down. The gas was stripped and stalled. The mass sailed on with the galaxies, which means it barely interacts even with itself. That's a measurable limit, and it's been getting tighter. Infrared imaging has now produced the sharpest mass reconstruction of the system anyone has made, built from a large catalogue of separate lensing constraints, without assuming in advance that mass follows light. It pushed the self-interaction limit down by a large factor. It also settled an old argument about the merger itself. The smaller cluster turns out to be a modest fraction of the larger one, in the same proportion a simulation had been forced to assume 2 decades ago in order to reproduce the shock speed.
The simulation was right about an input nobody could measure at the time. The oldest light in the universe says the same thing, by a route that has nothing to do with clusters, galaxies, orbits, or lenses. For the first few 100,000 years, the universe was opaque, not dark, blindingly bright and opaque, because it was hot enough that atoms couldn't hold together. Free electrons scattered photons constantly, so light couldn't travel any distance before being knocked sideways. Matter and radiation were locked into a single fluid. That fluid did what fluids do when you put a lump in them. Gravity pulled material toward a slightly over-dense spot. As material piled in, the radiation trapped with it pushed outward, harder and harder, until the pressure won and the region expanded again, at which point gravity started pulling it back. Compression, rebound, compression. Sound waves, in the most literal sense, running through the entire universe at a large fraction of the speed of light. Then the temperature dropped far enough for electrons and nuclei to combine into neutral atoms. The fog lifted in a geological instant. Photons stopped scattering and flew off in straight lines, and they have been flying ever since. They arrive now as a faint microwave glow from every direction. You are looking at a photograph of a standing wave. Every hot and cold patch in that image is a region caught at some phase of its oscillation at the moment the pressure vanished, frozen exactly as it was. That's what makes the pattern readable, because the patches sort themselves by angular size. Regions that had exactly enough time to reach maximum compression before the fog lifted produce the strongest variation at one particular scale. Smaller regions oscillate faster. Some had time to compress, rebound, and reach maximum rarefaction. Smaller still, and they got through a full cycle and were compressing a second time. The strength of the temperature variation, plotted against angular scale, comes out as a series of peaks alternating: compression, rebound, compression, rebound. And there was something else in that plasma, which ignored light entirely. It feels gravity, so it falls into the same overdense regions. But radiation pressure has no grip on it, so nothing ever pushes it back out. It just accumulates in the wells and makes them deeper. So the ordinary matter falling in gets extra help on the way down, and no extra help on the way back out. Compressions get boosted, rebounds don't. So the odd-numbered peaks in that plot rise relative to the even ones, and how much they rise depends on precisely how much of this stuff was present. The height of the third peak against the second is a direct measurement of it. That's it. The whole method is read the ratio, get the amount. The answer for ordinary matter comes out at the same 20th that the deuterium gave. The answer for the rest is the number this whole thing opened with. Two measurements with nothing in common. One from nuclear fusion in the first minutes, one from acoustics 300,000 years later, landing on the same figure. And the same data carry a harder argument, which is about why anything exists at all. The variations in that ancient light are tiny, 1 part in 100,000. That's how lumpy the universe was when the fog cleared. Gravity amplifies lumps, but slowly, and it can only start working on ordinary matter once the radiation lets go of it. Given the whole history of the universe, ordinary matter still doesn't get anywhere near the density contrast that a galaxy requires. It isn't close, and there's no more time to be had, because that's the entire history already spent. Something else had to have started earlier. Something that never felt the radiation pressure could begin clumping while the plasma was still ringing. And by the time the fog lifted, it had already dug deep wells across the sky. The gas didn't have to build structure from scratch. It fell into structure that was waiting. 5 independent methods, 1 number. Still no idea what the thing is. Which is why, starting in the 80s, the search moved underground. The reasoning runs like this. Our galaxy sits inside a roughly spherical swarm of the stuff, extending far beyond the visible disk. The disk rotates. The swarm doesn't, because it never lost the energy that would let it settle into a rotating plane. So the Sun, carrying us along toward the constellation Cygnus, is plowing through material that is essentially standing still. That makes a wind. It has a direction, and the direction is fixed against the stars. So as the planet turns, you spend part of each day facing into that wind, and part of each day drifting downwind, and the direction it comes from swings right across your sky. There's a slower rhythm on top of it. Earth's orbit is tilted to that flow, so for half the year, our motion around the Sun adds to the wind, and for the other half, it subtracts. The speed peaks in the first days of June and bottoms out in early December. The difference is small, but it's a signature. And it was proposed as one in 1986, because nothing else on Earth peaks in June for that reason. Catching a single particle of it requires removing everything else. Nearly a mile beneath the Black Hills of South Dakota, in a chamber cut into an old gold mine, sits a tank holding 10 tons of liquid xenon. The rock overhead absorbs the shower of particles that constantly rains through the surface. The cavern is the same one where solar neutrinos were first detected in the 60s, using a tank of dry cleaning fluid. Xenon is the target because it's dense, chemically inert, and contains no long-lived radioactive isotopes of its own. It's dense enough that a block of solid aluminum floats on it. Held just cold enough to stay liquid, watched from above and below by nearly 500 light sensors. A hit looks like this. Something strikes a xenon nucleus and knocks it sideways. The recoiling nucleus barges through the liquid and produces a prompt flash of ultraviolet light. It also strips electrons loose, and an electric field across the tank drags those electrons slowly upward through the liquid into a thin layer of xenon gas at the top, where they produce a second flash. 2 flashes, separated by a measurable delay. The delay tells you how deep in the tank the event happened. The pattern of light across the top sensors tells you where horizontally. Every event gets a position in 3 dimensions. And since xenon is dense, anything arriving from outside gets stopped in the outer layers. Only the core is quiet. Events there came from inside, or from something that walked through 10 tons of liquid, metal-dense noble gas without noticing it. The ratio between the 2 flashes tells you something else, whether what recoiled was a nucleus or an electron. Radioactive backgrounds mostly kick electrons. The thing being hunted would kick nuclei. That experiment ran for over 400 live days across 2 years of data, in the most sensitive configuration anyone has ever built. 0. Then, in 2024, detectors of this kind started seeing nuclear recoils. 1 under a mountain in Italy, 1 under a mountain in China, and the following year, the tank in the gold mine. The recoils are real. They are not dark matter. They're neutrinos from the core of the Sun, specifically from a rare branch of its fusion chain involving boron, bouncing off xenon nuclei. The first time anyone has watched a neutrino nudge a whole nucleus in a detector built for something else entirely. And that is the worst possible good news, because the event looks the same. A single nucleus recoiling. No second particle, no track, nothing to tag it with. Event by event, a solar neutrino recoil and the thing everyone is looking for are indistinguishable. You cannot shield against it. Neutrinos come through a mile of rock as though it were open air. Build a bigger tank and you collect proportionally more of them. Run longer and you collect more of them.
Every improvement that increases sensitivity to dark matter increases the neutrino count by exactly the same factor. 40 years of digging deeper and freezing colder ran into a flaw. Not a limit of engineering, which can always be pushed. A limit of physics, which cannot. It arrived in the room where solar neutrinos were first caught, 60 years after they were caught there. This time as the obstacle. None of that stopped the hunt. It fragmented it. Once the most natural candidate stopped looking natural, the field spread out across a range of possibilities so wide, it stops being a range and becomes an admission. And in the middle of that spread sits one experiment that has been reporting a positive result for over 2 decades, which nobody has managed to reproduce, and nobody has managed to kill. The setup is a stack of sodium iodide crystals, 1/4 of a ton of them, grown to extreme purity and sitting under a mountain in Italy. Sodium iodide scintillates, a recoiling nucleus makes a flash of visible light, and the crystal is watched for those flashes. The claim is not that they've identified individual events, it's that the rate of low-energy flashes rises and falls over the year, smoothly, peaking within days of where the halo wind puts the maximum. Over 22 annual cycles. The statistical strength of that oscillation is far beyond anything a physicist would normally demand before declaring a discovery. The problem is that every other experiment sensitive to the same range says there's nothing there. For years, the collaboration had a legitimate defense. Everyone else was using different target material, and comparing across materials drags in model assumptions about how the particle couples to different nuclei. 2 experiments were built specifically to remove that excuse. Same crystals, same technique. One under the Pyrenees in Spain, one in a tunnel in South Korea. Both ran for 6 years. Both see a flat rate. Combined, they exclude the original modulations strongly. The original collaboration has not withdrawn anything. There is no accepted explanation for what those crystals in Italy are doing. The seasonal backgrounds you'd reach for first. Atmospheric temperature, the muon rate through the rock. Peak weeks away from the observed maximum, which is why the thing has survived this long. That's where it sits. Unresolved, in public, for 1/4 of a century. The X-ray line has a cleaner arc, and it ends worse. Stacked across the spectra of dozens of galaxy clusters, a faint emission feature appeared at an energy where no expected atomic transition sits. One reading? A heavier, sterile relative of the neutrino, decaying into a lighter neutrino and a photon. Because the released energy would always be the same, every decay anywhere would emit at one fixed wavelength, and stacked across clusters, it would build into a line exactly like that. Settling it required spectral resolution that no X-ray telescope had. A satellite carrying that instrument reached orbit, took its first spectra of a nearby cluster, and then tore itself apart weeks later after a control failure spun it to pieces. Its replacement finally flew. It stacked 10 clusters at resolution far beyond the original detection and found nothing. That limit is several times tighter than the dead satellite managed, and still several times short of what it would take to rule the original claim out completely. Years more observing might close it. Axions differ in one respect that matters a lot. Nobody invented them for this. They came out of a problem in the strong nuclear force, which, by every theoretical right, should violate a certain symmetry, and, by measurement, doesn't, to a precision that looks absurd unless something is enforcing it. The proposed enforcement mechanism predicts a very light particle as a byproduct. Only afterwards did anyone notice that if such particles were produced in the early universe, they'd be cold, abundant, and essentially invisible. Catching one exploits a single trick. In a strong magnetic field, an axion can convert into a photon.
So you put a cooled resonant cavity inside a powerful magnet and tune it. If the cavity's frequency matches the axion's mass, the conversion is enhanced and a faint microwave signal appears. Tune, listen, retune. The most recent runs crawled across a narrow band. The full plausible range is orders of magnitude broader. And then there's the possibility that it isn't a particle at all. Black holes that formed in the first instant of the universe from density peaks that collapsed directly, long before any star existed. Microlensing has closed most of the available masses by the same technique that closed the dead stars. One window is still open. Objects with roughly the mass of a mountain and an event horizon smaller than an atom. Too small for a star's light to be measurably focused around them, too large to have evaporated by now. Everything currently on the table, lined up, spans about 90 orders of magnitude in mass. That's not a list of options. It's the width of the ignorance, written out. Now I owe you something, because I've been steering. Everything so far has been built on flat rotation curves as an established fact. Galaxies rotate too fast at their edges, therefore mass is missing, and the case is closed. Our own galaxy doesn't do it. Measuring the Milky Way's rotation from inside the Milky Way is hard, which is why the answer arrived so late. It took a spacecraft that measured positions and motions for well over 1 billion stars, precisely enough to build our own rotation curve out to roughly twice the radius of the bright disk. And out there, the curve comes down. It falls along the same slope the solar system shows, the fall-off you get when the mass has stopped growing. A flat curve is disfavored by the data. The Milky Way's total mass has been revised downward by a factor of 4 or 5. And I should say plainly, this is recent. It's argued over, and different teams working the same data still disagree about the outer points. It may turn out that our galaxy is the odd one.
It hasn't had a major merger in a very long time.
And a quiet history could plausibly leave it with a thinner outer halo than its neighbors. It is not a verdict. But the galaxy that taught everyone the lesson is the awkward case. And that deserves saying out loud rather than leaving in a footnote. There's a road not taken here. In 1983, someone proposed that nothing is missing, and the equation is wrong. Specifically, that below a certain very small acceleration, the relation between gravitational pull and resulting motion departs from Newton's. The acceleration in question is absurdly gentle. Drop something in a field that weak from rest, and it takes about 1.5 days to fall 1 meter. Nothing in the solar system ever gets that slow, which is why no local experiment contradicts the idea. Out at the edges of galaxies, it's the normal regime. That proposal has a record that gets undersold, so I'll put it straight. It predicted, before the data existed, that faint diffuse galaxies would show slowly rising rotation curves, while bright compact ones would decline to a flat value. Both turned out to be true. It produces the relation between a galaxy's total ordinary mass and its outer rotation speed as a mathematical consequence. And that relation is observed, tight, over an enormous range of galaxy sizes, with almost no scatter. Across large samples of disk galaxies, the gravitational pull you actually observe tracks the pull computed from visible matter alone along one single curve. That last point is the uncomfortable one. Halos are supposed to be assembled by chaotic individual merger histories. The visible matter should be a poor predictor of the total. Instead, it's an excellent one, and nobody has a clean account of why. Where the idea breaks is equally clear. In galaxy clusters, it still comes up badly short, which means a theory invented to abolish missing mass has a missing mass problem of its own. It cannot produce the alternating peak heights in the oldest light, because that pattern requires something present in the plasma that ignores radiation, and modifying gravity adds no such thing.
It has no mechanism to give structure the head start it needs. And the cluster collision, where the pole sits away from the matter, remains a direct problem for any version of it. One road explains galaxies elegantly and fails at everything larger. The other explains everything larger and has to be fitted, galaxy by galaxy, to reproduce what the first road predicts outright. And then a galaxy turned up with almost none of it. Two of them, actually, both faint, both very spread out, near a large elliptical galaxy. Diffuse enough that you can see background galaxies straight through them. Each has a population of globular clusters orbiting it, and the speeds of those clusters are so slow that the total mass required to hold them is about the mass of the stars you can see. There's essentially no room for anything extra. Then came the fight, and it was a fight about distance, the quantity that has been quietly deciding this entire subject since 1933. If the galaxy is closer than assumed, then it's intrinsically fainter, contains fewer stars, weighs less, and the anomaly evaporates. One group put it at a distance where it does, another put it half again as far, where it doesn't. The whole result hung on which was right. Settling it took 40 orbits of a space telescope, aimed at a single dim smudge, to measure the brightness of its oldest red giant stars. Those stars brighten as they age until they reach a sharp ceiling and stop. That ceiling is the same everywhere in the universe, which makes it a ruler. The measurement landed near the larger distance. The anomaly held. The same quantity that broke the founding measurement nearly erased this one. And this is what makes a galaxy without dark matter an argument for dark matter. If the extra pull came from a modified force law, no galaxy could opt out. Gravity applies to everything. There is no way to build a system where the law switches off. But if the extra mass is a substance, it's an ingredient. And ingredients can be removed. Simulations produce exactly these objects through close encounters with a massive neighbor. The halo is loosely bound and gets stripped away, while the stars sit deep in the middle, tightly bound, and stay. And that points at what this stuff really does, which isn't about galaxies at all. Ordinary matter can shed energy. Gas radiates, cools, sinks, and flattens into a spinning disk. That's why galaxies look the way they do, and why planets orbit in a plane. Something that doesn't interact with light has no way to lose energy. It falls in, overshoots, comes back out, and keeps doing that forever. So it never settles, and it never forms structures like the ones we live in. It stays a swarm, and that's precisely what makes it useful. A puffy, slowly assembled scaffold that holds a gravitational well open, while the gas does the interesting part inside it. Nothing about that arrangement was designed, and it isn't fortunate in any meaningful sense. It's just that a universe with only ordinary matter never gets past faint ripples, and there'd be nothing in it capable of noticing. The most precisely measured ingredient of the universe is also the only one nobody can name. Those two facts aren't in tension. They're what measurement without identification looks like, and physics has been in that position before. The periodic table was organized decades before anyone knew what an atom was made of, and it worked the whole time. The difference is that chemistry eventually got its answer. The next detector of the underground kind is already designed, 60 tons of xenon, with the stated goal of reaching the neutrino floor. That's an unusual thing to write into a proposal, because it means the machine is built to arrive at the point where the method stops working. There's no meaningful generation after it. That gives the field roughly one more decade of this particular approach, and then a decision. If nothing turns up, there's no crisis and no collapse. The evidence doesn't go away, because it never depended on catching a particle in the first place. Clusters still hold together.
The oldest light still shows what it shows. What changes is the character of the claim. It becomes something we can weigh precisely and map across the sky, while having no access to it beyond gravity. Some physicists think that's the actual answer, that the stuff couples to nothing else, and there was never a door to find. That would be a strange thing to accept, and there's no rule saying the universe has to give you more than one handle on something. 90 years on, that opening figure has more digits behind the decimal point than ever, and still nothing standing behind it. The honest, open question isn't whether it exists, it's whether it's knowable at all by creatures who can only ever poke it with the one force it happens to feel. Nobody knows how to answer that yet. The first serious attempt runs out sometime in the 2030s. If you got something out of this, a like and a subscribe do help.